All right, so here we go. Today is all about Quiz 4 review. So first up, we're graphing the rational function with at least 6 marked points. So just a throwback to what the parent looks like. Y equals 1 over x. And if I make my table of inputs and outputs, I input -3, -2, -1, 0, 1, 2, and 3. And then I output -1/3, -1/2, -1. If I input 0, it's undefined. Okay, 1, 1/2, 1/3. Okay, when I look at the structure, I see that negative out in front, so that tells me vertical flip. That 2 on top means vertical stretch by a factor of 2. Okay, here I see that that's 3 to the left, and then right here that's 1 unit down. So I start with my asymptotes. I'm going to go 3 left. So right here, there's an asymptote at x equals -3. And then down 1, there's my horizontal asymptote at y equals -1. Okay, so now when I plot the rest of my points, I know usually from where the asymptotes cross, I go over 1, up 1, but I need to flip it. So I'm going to flip it and then also stretch it. So I have to keep all of that in mind as I plot it. So maybe I'll start with my parent and I'll do the flip first. So if I do my flip, normally over 1, up 1, so over 1, down 1 puts me right here. Okay, and then I'll go over 2, down 1/2, over 3, down 1/3, and then here I would go over 1/2 and down 2, over 1/3 and down 3. Okay, so those are my parents, but with the vertical flip. Okay, over here, over 1, up 1, over 2, up 1/2, over 3, up 1/3, so then over 1/2 and up 2, over 1/3 and up 3. Okay, but now the stretch. So everything doubles. So if I start with this branch here, right, normally here I'm up 3, right, over 1/3 up 3, but I'm going to double that to make that 6. Here, the up 2 becomes up 4, up 1 becomes up 2, up 1/2 becomes 1, up 1/3 becomes 2/3. So there's my first branch, like that. Okay, and then over here, if I start with this one, right, 3 away becomes 6 away. 2 away becomes 4 away. 1 doubles to 2. 1/2 doubles to 1. 1/3 becomes 2/3. And there's my second branch. Okay, my domain, I'm saying anything but -3. So -infinity to -3. Union, -3 to infinity. My range, y can be anything but -1. So -infinity to -1. Union, -1 to infinity. My horizontal asymptote is at y equals -1. My vertical asymptote is at x equals -3. Okay, next I need to use long division to rewrite this function in transformation form. So here I'm going to take that x minus 2, I'm going to divide it out of the -4x plus 3. Build the structure. Okay, so now x times what is -4x? Well, -4. Okay, multiply it back over these two terms, and we get -4x plus 8. Okay, so -4x minus a -4x, that zeroes out. 3 minus 8 is -5. So this would be g of x is equal to -4 plus that remainder of -5 divided by x minus 2. But usually I whip that around and I rewrite that as g of x is equal to -5 over x minus 2 take away 4. right? It helps me see the transformations a little bit more clearly. Okay, and then when I state them, I see a vertical flip, right? That's the negative. A vertical stretch by a factor of 5. Okay, and then I see 2 to the right and 4 down. Okay, next up, when it's more complicated, can we find all of these features? And then can we graph it using at least 6 marked points? So the first thing that I do when I look at it in this structure where it's a polynomial over polynomial is I factor it down. So on top, I can divide out that -1, that GCF, and then I have x squared plus 9x plus 20. On bottom, I can factor that down here. I can make that x plus 5 times x minus 3. Okay, and then one more step on top. So I have a -1, and then parentheses, x plus 4 times x plus 5. And the bottom already factored is x plus 5 times x minus 3. So I can see that I can reduce down x plus 5 and x plus 5 because anything over itself is really just 1. So nicely cleaned up, this looks like -1 times x plus 4 over x minus 3. Okay, so now my vertical asymptote or asymptotes, I'm looking at what stayed behind right here. So that's going to present as an asymptote at x equals 3. Okay, any whole is what cancels away. So I'm going to have a whole right here at x equals -5. I just need to figure out what's the y value that goes with it. So I'm going to plug in an x value of -5 into this structure right here and see what it outputs for y. So y equals a -1 times -5 plus 4 all over -5 minus 3. Okay, so I have a -1 times a -1, so that's a +1 over -8. All right, so the output is -1/8. So that tells me my location of the whole, -5, comma, -1/8. Okay, my horizontal asymptote, is it top heavy? Then I wouldn't have any asymptote, any horizontal asymptote. Is it bottom heavy? Do I have a bigger degree term on the bottom? Then it would be y equals 0. Or is it the same degree? Here it's the same degree because I have a quadratic over a quadratic. This is same degree. So when it's the same degree, we divide out those coefficients, those leading coefficients. So a -1 divided by a +1 is just a -1. So y equals -1. All right, my x-intercept always comes from any factor that remained on top. So if I set this x plus 4, make it equal to 0 and solve, I get that x equals -4 when y is 0. Okay, my y-intercept, that's when x is 0. So if I plug in back into here an x value of 0, I have -1 times 0 plus 4 all over 0 minus 3. I get -4 over -3, which is just 4/3, or 1 1/3 if that's easier to graph. I think that is. All right, I have all of my features, so now I'm ready to start graphing. So when I look at, let's see, the asymptotes, vertical asymptote at x equals 3, so right here. Horizontal at y equals -1, so right here. Okay, then I'm looking at where's that hole. That hole is at -5, so -5, -1/8. So right here, nice and hollow. So now if I try to mirror that on the other side, how did I get there? I went left here, left 8, and then would be up here from this asymptote, right? Because I'm starting from here. So left 8 up, that would be 7/8. So here I'm going to go right 8, so it puts me about here, and then down about 7/8. So I'm going to put a little dot right there. It's a little bit off, but that is okay. Close enough. Okay, then my next point to plot would be the x-intercept, so -4, 0. So it puts me right here. So from where the asymptotes cross, right, that's left 7 and up 1. So I need to go right 7 and down 1. Puts me right there. Okay, and then I have the y-intercept 0, 1 1/3. So 0, 1 1/3 puts me right here. Okay, so from where the asymptotes cross, that's left 3 and up 2 1/3. So I need to go right 3 and down 2 1/3. So about right there. Okay, if we ever needed more points, we know what to do. If I look at this asymptote right here, I'd pick a point maybe to the left or to the right of it, and that would give me another input for x to find the output for y, and just one more point to smooth out my curve. This is enough. This is plenty, right? So here is my first branch, and then here is my second one, like so. Okay, next we're solving rational equations. So the first one, we see a ratio equal to a ratio. It's a basic proportion, so easy to solve by just cross multiplying. I always first just look at my domain restriction, because if that shows up in my answer, I know that it doesn't actually work. So if I set this equal to 0 and I solve, I would see that x cannot be -3. Same thing here. So let's tuck that in, that x cannot be -3. It can be anything else, just not -3. So then when we cross multiply, we have x minus 1 times x plus 3 equals x minus 4 times 2x plus 6. Okay, we've got to FOIL out the left, first outer, inner, last. So here I have x squared plus 3x minus 1x, so really plus 2x, and then last is minus 3. Okay, on the right, first, outer, inner, last. So that first is 2x squared. The outer is plus 6x. The inner is minus 8x. So minus 2x overall. And then the last, I have a minus 24. Okay, combine like terms. So let's pull to the right. Let's subtract the x squared over. Subtract the 2x over. And add the 3 over. So now we have our equation equal to 0. So 0 equals x squared minus 4x minus 21. And if I factor from here, that should be x minus 7 times x plus 3. Okay, so my two possibilities, x could be 7, x could be -3, but go back to that domain restriction that we saw early on, and we see that it can't actually be -3, or it would make the denominator equal to 0, which makes the whole thing undefined. So the only solution that works is x equals 7. All right, next one here, we see it's just a little bit more complicated, because now we have two separate ratios on the left joined with addition equal to this one ratio on the right. So here we want to clear our fraction. So I'm looking at what does this first denominator here look like factored, because here these are already just simple binomials. So if I factor this first, I see that that is x plus 5 times x minus 3. Okay, I'm just going to cross that out so I can see it factored. So now I know that my domain restriction is that, well, x can't be 3, x can't be -5, and it's the same thing I'm seeing here. So whatever I solve for, I can't have -5 or 3 as solutions. Okay, so now I want to clear my fractions by multiplying each term by that common denominator, which has to be x plus 5 times x minus 3. So I'm going to go ahead and write x plus 5 times x minus 3 here, and then here again, and one last time. All right, so then I can see that it's going to cancel out these x minus 3's. For here, these x plus 5's, right? Anything over itself is just 1. And then over here, the x plus 5 and the x minus 3's. Okay, so now here I have x times x plus 5. Okay, plus 2 times x minus 3 equals negative 16. All right, so now I need to distribute. I get x squared plus 5x plus 2x minus 6 equals negative 16. Okay, combine like terms and pull everything to one side. So let me add the 16 over. X squared plus 7x plus 10 equals 0. And now I factor. Oops, 2. X plus 2 times x plus 5 all equal to 0. Let me make that look nice and pretty. And then we're good. All right, so x plus 2 times x plus 5 all equal to 0. And then when we solve, we get that x equals negative 2, x equals negative 5. And then when I look back at my domain restriction, I see, oh, no, can't be negative 5. Because if it was, if I plugged that back in, say here, that would make the bottom equal 0, and we know that that would make it undefined. So my only solution that works here is the solution of x equals negative 2. All right, next up, here giving you a complex fraction, right? We have a fraction inside of a fraction, and we're asked to simplify. So if I look at the 3 separate fractions that we have, or ratios, this one has an x on the bottom, this one has an x minus 1 in the bottom, and this one, if I factor that, that's 2 times x minus 1 on the bottom. I'm just going to cross it out so I can see it factored. All right, so then overall, what is my least common denominator? What could I create that would make them all the same, right? This one has an x, this has an x minus 1, and this one has a 2 times x minus 1. So I'm going to need a 2. I'm going to need a 2. Let me just write this out, LCD. A 2, right? Because this one has a 2, but this one has an x, so it's going to have an x as well. And then these have an x minus 1. So there we go. That is the LCD, 2x times x minus 1. So I'm going to multiply here 2x times x minus 1 over here 2x times x minus 1. All right, so I'm going to multiply this times the 3 over x and times the 5 over x minus 1 first. So now in my next stage, 3 over x times 2x times x minus 1. Really, it's the x's that are going to cancel out to 1. So 3 times 2 becomes 6 times x minus 1. Okay, and then I'm multiplying the 5 over x minus 1 times the 2x times x minus 1. The x minus 1's will cancel away. So 5 times 2x is 10x. All right, so that's what I have right now on top, all cleaned up. Now on bottom, let me kind of block this out of view for a moment. Here I'm multiplying 1 over 2 times x minus 1 times 2x times x minus 1. So here the 2's will cancel away, the x minus 1's will cancel away, and I'm really just left with x. So there we go. Now I just have to resolve that. So I have to distribute that 6. So I have 6x minus 6 plus 10x over x. So I have now 16x minus 6 over x. And I can divide out a 2. So 2 times 8x minus 3 all over x. Okay, I can leave it like that. That's fine. It's fully factored. I'll always take that. Or you could just leave it back in standard form, nothing reduced. So 16x minus 6 all over x. Either format is fine. Okay, next, finding an inverse. So here we know to flip the x and y values. So I'll say that x equals -3 over y plus 5 plus 6. Okay, so next stage I would take away the 6 from each side. X minus 6 equals -3 over y plus 5. Okay, I want to clear the fractions, so I'm going to multiply both sides by y plus 5. And just to see things clearly, I'm going to keep it in parentheses. And just a reminder that that's also in parentheses, right? So I don't want it to look like I'm multiplying a monomial. I really have a pair of binomials that are being multiplied here. And these canceled away. So now, if I just write that cleaned up, I have y plus 5, right? That package times x minus 6, that package equals -3. But I want to get the y by itself. So I'm going to divide by x minus 6. So now y plus 5 equals -3 over x minus 6. And then I'm just taking away the 5. Okay, and I've done my job. I'm just going to write it in function notation. So inverse of function f, right, like that. I slide that over. And I get -3 over x minus 6. And then take away 5. All right, and that is it. So let's flip our page, go to the back. Okay, I have a little practice with logs again. Don't want you to lose those skills. So let's start there. So here I want to condense first, and then we'll expand. So if I condense, I want to turn it into a single log. So that 5 will go back in the exponent position, and so will that 1/4. So right now I have log base 3 of x to the 5th plus log base 3 of x really to the 1st minus log base 3 of x to the 1/4. Okay, so if I fuse these two together, right, they're joined by addition, so I can multiply the x to the 5th times x to the 1st, which gets me x to the 6th. So log base 3 of x to the 6th minus log base 3x to the 1/4. So if I want to join these together, then I'm going to take these two arguments and I'm going to divide them. So log base 3 x to the 6th over x to the 1/4. Okay, and then I'm going to subtract the small from the large. I'm going to subtract the 1/4 up. So I'm looking at what's 6 minus 1/4. So if I want to create that common denominator, I'm really multiplying by 4 over 4. So now I have 24 over 4 minus 1/4, which is 23 over 4. So I end up with log base 3 of x to the 23 over 4 power. Okay, then I'm going to expand it. So over here, we're going to expand this logarithm. So here I start off with the fact that it's a quotient, a fraction. So I'm going to split it into log base 16 of y squared minus log base 16 of 4x. Okay, but this is really here still a product, so I want to separate that into two logs using addition. So now I'm going to also pull that 2 out in front while I have a moment. So 2 times log base 16 of y, okay, minus, I'm going to put parentheses here, log base 16 of 4 plus log base 16 of x. Okay, I put that in parentheses so I can keep this together right here because that would multiply back to become a product right there. Okay, and then I can resolve this part right here because I know that 16 to a certain power gets me 4. I know that the square root of 16 gets me 4. So 16 to the 1/2 power gets me 4. So one more step, 2 times log base 16 of y minus parentheses 1/2 plus log base 16 of x. Right, you can leave it like that. That would be fine. Or if you wanted to distribute that minus right here to both terms, you could leave it as 2 times log base 16 of y minus 1/2 minus log base 16 of x. Both of those options are fine, equally correct. Either way. All right, next up, find the expression that makes the following true. Okay, so here I see that I have this ratio or this package here divided by whatever goes here equals this part right here. So I think what makes sense is let's first factor everything and look at what's missing. So right here I have x plus 3 over x minus 6 times x minus 2. Okay, it's divided by this, so I'm just going to go ahead and say times and flip it, and then factor that x squared plus 3x minus 10, that trinomial. That's going to factor into x plus 5 times x minus 2, right? We don't know what that bottom piece is going to be yet, equals x plus 5 over x minus 6. All right, so there's my big expression, and I'm trying to find the missing piece. Okay, so if I look at what it could reduce right now, I see that these x minus 2's, those can cancel right there. So right now I have x plus 5, and I have x minus 6, which is what ends up over here. So I'm going to need that x plus 3 to cancel away by putting an x plus 3 right there, right? Because then I'd end up with that x plus 5 over x minus 6. So that missing binomial must be x plus 3 right there to make it all work out and be true. Okay, next I'm simplifying another complex fraction. So first thing to look at is the numerator is just b minus a, and the denominator has these two separate terms that both have a negative exponent. So I need to resolve what is a to the negative first power, that's 1 over a, and then b to the negative first power is 1 over b. So let me first rewrite it as b minus a over 1 over a minus 1 over b. Okay, so now looking at overall, what would be my common denominator between anything where there's a fraction? And that would just be a times b. So I'm going to go ahead and multiply the top and bottom by a times b. So here on top, that a times b really doesn't have to clear anything. So I'm just multiplying it by the package of b minus a. And then over here, I'm going to multiply by those two separate terms to clear the fractions. So now I'm going to have ab times b minus a on top over. Okay, so if I have 1 over a times ab, those a's cancel away and I just get b. And then over here, I know there's a minus. So here I have 1 over b times ab. The b's cancel away. I'm just left with a. Okay, so now what happens? Those b minus a's, they are stacked over each other, right? And anything over itself is just 1. So I end up with just AB as my final answer. That's as simplified as I'm going to get. All right, back to some log application problems. Let me slide up here. Slide that over. Okay, so here a fossil found on an archaeological dig contains 68% of its original carbon-14. We are given our equation, our model, for the decay of carbon-14, and we want to estimate the age to the nearest hundredth. So we know, again, 68% of its original carbon-14, right? That N naught right there represents the original amount. So we're saying, okay, currently we have 0.68 times that original amount, and then I'm just transferring the right-hand side of my equation. Okay, so that N naught cancels away, and I'm really left with 0.68 equals e to the negative 0.00012 t power. So now if I rewrite this as a log, I know it's log base e, so ln 0.68 equals negative 0.00012t, and then I can divide that negative 0.00012 from both sides. All right, so when I type that in, I'm going to get my answer. I just want to record it to 2 spots. So here, ln 0.68 divided by negative 0.00012. And there we go. So record it to 2 spots. We would say 3,213.85 years old. All right, next one. The initial population of bacteria in a lab test is 250. The bacteria grows at a rate of 85% every 20 minutes. And we want to find the population at the end of 3 hours. So whatever our final amount is, it's going to be our starting amount, our initial amount, times 1 plus, because it's growing, that rate of 0.85. And then it's just how many times, what's my exponent here? So how many times is it going to have that growth over this span of time? So it's saying every 20 minutes is when it grows at this rate, and we want to find the population at the end of 3 hours. So in 3 hours time, right, that means that we're going to see 9 20-minute periods. So 20 minutes in 1 hour happens 3 times. So in 3 hours, it happens 9 times. So that's really what I'm going to plug in. So I'm looking at, well, what is 250 times 1.85 raised to the 9th power? So here we would say that is about, we want nearest whole number. So 63,450, that 0.88, right, it's going to pull that up to an 8 right here. So 63,458 bacteria. All right, write the first 5 terms of the sequence. So here, when we're doing that, we're literally just plugging in. So we're looking at what's the first term all the way up to the 5th. All right, so I'm looking at 3 to the 1 minus 2 power, 3 to the 2 minus 2 power, 3 to the 3 minus 2 power, 3 to the 4 minus 2 power, and 3 to the 5 minus 2 power. So if I clean that up, that's saying 3 to the negative first, 3 to the 0, 3 to the first, 3 to the second, and 3 to the third. So we would get 1/3, 1, 3, 9, and 27, right? All makes sense, just powers of 3. Okay, next, writing a rule for the given sequences. Okay, so here I note that a sub n equals, okay, see, they're all fractions. Now on top, it's really just a 5, so here's a 5 right here. And then on the bottom, we see that we are starting with a 2, and then here this is 4, and then 8, and then 16. So here, when I run through kind of what my options are, I see that it's not increasing by a set amount, right? It's not jumping up by increments of 2, but I do see that it is doubling from stage to stage, which makes me think that it's powers of 2, right? This is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So if I do 2 to the n, like that, let's see if that works. If I plugged in a 1, I would get a 2. A 2 would get me 4. A 3 would get me an 8. So I have my rule. Okay, the next one here, it looks like if I didn't have different signs, it would look like it's increasing by increments of 5. But I do have signs that are flipping. So I know it's going to be one of those variations where it's going to be -1, either to a power that's going to make it start with a negative or flip to a negative on the second term. And since it's the first term, then I'll leave it as -1 in parentheses to the nth power, right? Because if I put a 1 here, that will keep it negative. And then since it's moving up in increments of 5 otherwise, it would be just 5n if it was an arithmetic rule. So let's just check that to make sure that that works. So if I plug in a 1, this would be -1 times 5, so -5. If I plug in a 2, that 2 here would make this +1 times +10, 10, right? So we see that it holds. That must be our rule. All right, next one. Can we write using summation? So we see that giant E, that uppercase sigma. So here's my uppercase sigma. We'll say n equals 1 to start. We have 5 terms, so we put a 5 right here, and then just write the rule. So here I can see that from 6 to 13, I'm adding 7 again, right? And that is staying constant. I'm adding increments of 7. So I know that it's arithmetic. It has to be 7n. And then if I start with an n value of 1, right, then I'm at 7. What do I need to add or subtract to get back to 6? I need to subtract 1. So let me just double check that that rule holds. If I plug in a 1, it gets me a 6. If I plug in a 2, 14 minus 1 is 13, and so forth. All right, there is my series in summation notation. Okay, this next one here, I see that it goes ... So it keeps going to infinity. So I'll start with n is 1 to infinity, but building the rule, I can see that on top, it's just going 1, 2, 3, 4, 5. So we'll say that's just n. And then on the bottom, it's always 3. So we'll leave a 3 on the bottom just like that. And then that's it. Okay, and then lastly, can we find the sum? So we're saying find the sum of terms 1 through 6. So I want to go ahead and I want to write out first term up through 6th term. And then go ahead and plug in. So I have 1 squared plus 2, 2 squared plus 2, 3 squared plus 2, 4 squared plus 2, 5 squared plus 2, and 6 squared plus 2. All right, so 1 plus 2 is 3, 4 plus 2 is 6, 9 plus 2 is 11, 16 plus 2 is 18, 25 plus 2 is 27, 36 plus 2 is 38. Okay, and then I just got to add them up, add them up, add them up. And when I add all those guys up, they sum to 103. All right, have a good rest of your day, you guys.